Hey Voyagers, welcome back. You know what I was thinking about this morning? I was rewatching Interstellar for probably the 20th time, and something hit me like a wave I couldn't see coming. We spend so much time marveling at the cinematography, the music, the emotions, the performances, but what if I told you that every single frame is built on actual physics? Not made-up physics, not science fiction hand-waving, real equations, real science, Nobel Prize level science. Christopher Nolan's Interstellar isn't just the most scientifically accurate sci-fi film ever made. It's a love letter to physics itself. Written by Kip Thorne, a physicist who won a Nobel Prize for literally detecting gravity waves, the same gravitational waves we're about to talk about. But here's what's been bothering me. Even with Thorne's genius guiding every frame, the film compresses, it dramatizes, it simplifies, and I think we deserve to understand what's actually happening beneath the surface. Not because the movie is wrong, but because the real physics is even more mind-bending than the drama. It's more beautiful, more terrifying, more profound. So today, we're going on a complete journey through the interstellar universe together. We're going to decode every equation, every gravitational phenomenon, every paradox. We're going to ask the hard questions. Why do planets get pulled into tidal bulges? How can a human survive crossing an event horizon? What does it mean to exist in 5 dimensions? And by the end, you're going to understand not just Interstellar, but how the universe actually works. From the Blight destroying Earth to the Einstein-ROSEN bridge, from Miller's planet, where time is literally a weapon, to the 5D tesseract and the quantum data that saves humanity. Ready? Let's dive in. The movie opens on Earth gasping for breath, and I mean that literally. We see a global crop failure, civilization on the edge of collapse, and it's caused by something called the Blight. Now here's what most people don't realize. This isn't just a plot device thrown in to create drama. This is a scientifically grounded biological catastrophe. It's so plausible that it's actually terrifying. To understand why the Blight is so lethal, we need to go on a little journey together into something most people never think about: Earth's nitrogen cycle. Stick with me. I promise this is about to get terrifying. Our atmosphere is 78% nitrogen, more than 3/4 of the air we breathe. Crazy, right? We're literally surrounded by this massive reservoir of nitrogen. We can't use it. Humans, animals, most Earth life. We breathe oxygen. We're surrounded by this massive reservoir of nitrogen we can't touch. It's like being thirsty in the middle of the ocean. So the question becomes, and this is the crucial question, how do plants get the nitrogen they need? The answer is bacteria. Incredible little creatures called nitrogen-fixing bacteria live in soil. They do something absolutely remarkable. They take atmospheric N2 and convert it into usable compounds, ammonia, nitrates. These are the currency of life. Plants absorb these compounds, we eat the plants, we die, we decompose, the nitrogen goes back to soil, the cycle continues. For billions of years, this cycle has been the heartbeat of life on Earth. It's the most fundamental rhythm of existence. But what if something broke that heartbeat? The Blight. The film describes it as a nitrogen-consuming pathogen. And here's what that means, why it's so incredibly lethal. The Blight doesn't destroy the nitrogen, It metabolizes it. It eats the nitrogen compounds in soil that plants desperately need, and it does it faster, much faster, than soil bacteria can replace it. So, plants die, not because they lack sunlight, not because they lack water, but because the one nutrient they absolutely cannot live without, nitrogen, is being consumed faster than nature can replenish it. This isn't starvation, this isn't drought, this is a targeted attack on the foundation of Earth's food chain. It's genius, it's terrifying, it's beautiful in its ruthlessness. Let's trace what happens next, the cascade, the collapse. Step 1. Nitrogen depletion. The blight consumes fixed nitrogen in the soil. Plants cannot absorb these compounds because the blight got there first. Result? Global plant death. Not tomorrow, not gradually, but inevitably, regardless of how sunny it is, regardless of rain. Nothing can save them, nothing. The food chain is severed at its root. Step 2, photosynthesis collapse. Now, plants aren't just food. They're the primary producers of our entire biosphere. They perform photosynthesis. You know that equation. 6 CO2 plus 6 H2O plus light yields C6H12O6 plus 6 O2. This reaction produces two critical things, glucose, food, and oxygen. But if all plants die, if photosynthesis stops globally, then both production lines shut down. Without photosynthesis, oxygen production ceases. The atmosphere stops being replenished. Carbon dioxide accumulates in the atmosphere with nothing to absorb it. And the atmosphere becomes toxic to every oxygen-breathing creature on the planet. This is true, final suffocation. And here's what gets me, what keeps me up at night. We're watching this happen in real time, right now. Industrial agriculture, synthetic fertilizers, soil degradation. Interstellar isn't warning us about a fictional future. It's a mirror held up to our own world. So when we see those dust storms in the film, those dead crops, Cooper driving through an apocalypse, we're not watching fantasy. We're watching a scientifically plausible collapse, a warning wrapped in cinema. Jump forward in the film, we see something even stranger, something that gives me chills every single time. Cooper's autonomous farming machines wander off their programmed paths. They're drawn by something invisible, something he calls a gravitational anomaly. But then, this is the moment. In Murph's room, gravity seems to arrange dust into binary coordinates, precise, intentional, almost like a message written in the language of gravity itself. And here's what we need to understand. What's really happening here? In classical mechanics, gravity from a mass follows what we call the inverse square law. Gravity weakens with the square of distance. It's predictable, it's consistent. From any given mass, gravity behaves the same everywhere. But for gravity to fluctuate and push dust into patterns without a visible mass source, that violates everything we know about classical gravity. That tells us something else is happening, something from outside our normal reality. Imagine being a 2D stick figure on a piece of paper. You live in a flat world, 2 dimensions, that's all you know. And then something impossible happens. A circle appears out of nowhere. It grows, it shrinks, it vanishes. You wouldn't understand it. You couldn't see it. All you'd perceive is the cross-section, a circle that shouldn't exist in your 2D universe. Now, scale that up. We're 3D beings. If a 4D or 5D being, or technology from the future, interacts with our 3D world, they would create ripples of space-time curvature that manifest as gravitational anomalies. They would write messages in gravity. The dust in Murph's room forms a pattern analogous to something called a Chladni plate. Have you ever seen one? It's mesmerizing. Sand vibrates on a metal plate, and it arranges itself into geometric patterns. But here's the thing. The sand settles at the nodes, places where the vibration amplitude is zero. The sand is pushed away from high-amplitude vibration regions. Here, dust moves away from high-curvature space-time regions and settles in regions of minimum curvature fluctuation. The dust becomes a medium, a canvas. Gravity writes mathematics into the air. And these patterns encode something. They communicate. They guide Murph to NASA. They save humanity. This is the first hint that someone or something from outside our timeline is trying to save us. Someone is reaching across the fabric of reality to help us. And the physics? The physics is real. Speculative, yes, but grounded in relativity. Pretty incredible, don't you think? And then they reach Saturn, and they find it. A wormhole. But not how you might imagine it. Not a twisting tunnel you can see inside. Not the wormhole from every sci-fi movie where people fly through a vortex. A sphere. And when Romilly describes it, when she explains the physics, something profound happens. The film shifts. We're no longer watching action. We're watching a physics lecture. And somehow, it's more beautiful than any explosion could ever be. Here's the fundamental thing we need to understand. We've all been taught that space is fixed. Distance is distance. To get from here to there, you travel the distance. It's intuitive. It's how our brains work. But what if I told you space isn't fixed? What if I told you gravity can reshape the geometry of space itself? That's not science fiction. That's literally Einstein's General Relativity. The Einstein field equations are the foundation of everything we're about to talk about. G mu nu plus lambda g mu nu equals 8 pi g over c to the fourth power times t mu nu. I know, it looks intimidating, like the kind of mathematics that breaks brains. But here's what it means, and this is the beautiful part. G mu nu this is the curvature of space and time. T mu nu this is matter and energy. The equation says matter and energy curve space-time, and curved space-time tells matter and energy how to move. We live in a universe where nothing is fixed. Everything is relationship. Everything is geometry. Everything curves. Normally, to travel from point A to point B through space, you travel distance d through flat space-time. ds squared equals minus c squared dt squared plus dx squared plus dy squared plus dz squared. This is the Minkowski metric, how space behaves when nothing is warping it, when geometry is ordinary. But what if space isn't flat? What if it's folded? A wormhole rewrites the geometry of space-time itself. Instead of space being flat, it's shaped like a tunnel that connects two distant regions. It brings two galaxies, our galaxy and Andromeda, close together. Billions of light years become accessible. But here's what gets me, and I think this is one of the most brilliant observations in the film. Why is the wormhole a sphere? This is brilliant observation. This is physics literacy on display. If you draw a circle on 2D paper and fold the paper to create a tunnel, the mouth of the tunnel is a 1D circle. We live in 3D space. If you take 3D space-time and fold it through the fourth spatial dimension, or through the bulk as the film calls it, the mouth of the tunnel must be a 3D shape. The 3D analog of a circle is a sphere. It's mathematics, it's geometry, it's beauty, expressing itself through physics. When Cooper looks into the wormhole, he's seeing light rays from Andromeda being bent by the intense curvature. Light doesn't travel in straight lines near a wormhole. It follows the curves of space-time itself, so we see both sides of the galaxy. It's the most beautiful visualization of a mathematical concept I've ever witnessed on film. The mathematical description of this is called the Morris-Thorne metric, named after Kip Thorne himself, the movie's scientific advisor. He literally had to invent the math to describe this wormhole for the film, where L is your distance along the tunnel, from one mouth to the other. BO is the throat radius, how narrow the tunnel is at its tightest point, and theta and phi are angular coordinates. Here's the magic. If you travel the L coordinate from one mouth to the other, you traverse billions of light years instantaneously. The wormhole shortcuts space-time. But there's a catch. The Einstein field equations allow wormhole solutions. They're mathematically valid. The equations don't forbid them. But they require something we call exotic matter. Matter with negative energy density. And here's the problem. We've never observed exotic matter. We're not even sure it exists. So the wormhole is theoretically possible, but practically, with our current understanding of physics, it's probably impossible. Which makes you wonder, if future humans can solve this problem, what else can they do? What becomes possible if you can master the geometry of space-time? Notice the distortion as the Endurance enters? That's gravitational lensing made visible. The wormhole's curvature is so extreme that it bends light and literally warps the geometry of objects passing through. Not just beautiful cinematography, that's accurate physics. Crossing that threshold is crossing a topological defect in space-time, a point where space is literally folded in on itself. Then, when they emerge on the other side, they're in a foreign galaxy, and they're facing something even more terrifying than a wormhole. They're approaching a supermassive black hole. Here's something I genuinely love about this film. There's no magical gravity generator, no hand-wavy technology, no unexplained force fields. The Endurance creates artificial gravity the way we could implement it today. We're just talking about rotating the entire ship. When something rotates, the outside pushes outward. You experience this every time you go around a curve in the car. The seat pushes you outward. Your body wants to keep going straight, that's inertia, but the seat forces you into circular motion. Inside a rotating spacecraft, that push feels exactly like gravity. And that's not coincidence, that's physics. To replicate Earth's gravity, we need to balance centripetal acceleration with gravitational acceleration. So we have omega, how fast it spins, r, the radius, and g, Earth's gravity, 9.81 meters per second squared. According to official interstellar design materials, the Endurance has a radius of approximately 32 meters. Let's figure out how fast it needs to spin. After doing some calculation, show on screen, we got the actual Endurance. It rotates at approximately 5.6 RPM. Perfect! Match! That creates approximately 1 gravitational acceleration, 1 g, at the outer ring. Comfortable for long-duration spaceflight. The crew can eat normally, sleep normally, their bodies don't atrophy from 0 g. And here's what's elegant about this design. Acceleration isn't uniform like it is on Earth. It's proportional to distance from the center. At the hub, the axis of rotation, omega, is 0, so there's no artificial gravity. You're in 0 g. You float. As you move toward the outer ring, gravity increases linearly. At the outer ring, full 1 g. And this variation is actually closer to Earth's gravitational structure than uniform gravity would ever get. It's more realistic than most sci-fi ever gets. But it also creates problems, and we're about to see why. Now we meet Gargantua. Not a regular black hole, not even a large black hole. This is a supermassive, rotating black hole, what we call a Kerr black hole in extreme rotation. And when you see it on screen, what you're looking at is one of the most accurate scientific visualizations of a black hole ever filmed. Not an approximation, not an artist's guess. Actual physics. Look at the disk of light swirling around it. That's the accretion disk, matter spiraling inward toward the black hole. As it accelerates due to gravity, friction heats it to millions of degrees. The disk glows in X-rays and visible light. What you see in the film is a dramatization, but the physics is sound. But here's the thing that blows me away. Notice the light going over the top and under the bottom? That's gravitational lensing. Gravity is so immense that it bends light itself. Light doesn't travel in straight lines near a black hole. It follows geodesics, the shortest paths through curved spacetime. The black hole's gravity is bending those paths so dramatically that light from behind the black hole curves around and reaches us. We literally see both sides of the accretion disk. We see both sides of something we should not be able to see through. That creates what's called an Einstein ring, a halo of light around the black hole's shadow. It's one of the most visually stunning and physically accurate aspects of the film. And then there's something else. The left side is brighter than the right side. Not randomly, not cinematography, physics. The matter in the accretion disk on the left side is moving toward us at relativistic speeds, a significant fraction of the speed of light. The matter on the right side is moving away from us. When an object moves toward you at relativistic speeds, near light speed, its light undergoes blue shift. The wavelengths get shorter, the frequencies get higher. the photons carry more energy. Additionally, due to something called relativistic aberration, the radiation actually concentrates in the direction of motion. The light is beamed forward. We call this light beaming. For matter moving at even 0.9 c, 90% of the speed of light, this factor is dramatic. We're talking 10x increase in frequency for head-on approach. This is why the accretion disk isn't uniformly bright. It's a living visualization of relativistic motion made visible. What you're seeing isn't just beautiful, it's actual astrophysics playing out in real time. But it's about to get much more interesting. Because we're not just observing from a distance. They're approaching the edge of forever, much closer. And then Cooper says something, one line, one sentence, but it might be the scariest line in the entire film. 1 hour on the surface is 7 years outside. 7 years, gone, in 60 minutes on the planet below. Do you feel that? That's not just a plot point. That's an existential statement about the nature of time itself. This is gravitational time dilation, and it's one of the most profound predictions Einstein ever made. Here's the fundamental truth. Time is not absolute. Time is not some universal constant that flows the same everywhere. According to General Relativity, time passes at different rates depending on the strength of the gravitational field. The stronger the gravity, the slower time passes, relative to an observer far from gravity. This isn't about time feeling different, we're talking about time actually being different. If you spend an hour on a planet in intense gravity, your watch advances 1 hour, but someone far away from gravity, their watch advances 7 years. It's not relativity of motion, it's relativity of gravity itself. For a non-rotating black hole, what's called a Schwarzschild black hole, the time dilation formula is delta t prime equals delta t square root of 1 minus 2gm over rc squared, where delta t prime is the proper time on the planet, the slow time. Delta t is the time experienced far away, the fast time. G is the gravitational constant, m is the black hole mass, c is the speed of light, r is the orbital radius, and rs is the Schwarzschild radius, the event horizon. Now, to get a time dilation factor of 60,000, which is 1 hour equals 7 years, let's work backwards and see what orbital radius we'd need. 60,000 equals 1 over the square root of 1 minus the Schwarzschild radius divided by r. Solving. The square root of 1 minus the Schwarzschild radius divided by r equals 1 over 60,000. Schwarzschild radius divided by r, approximately 0.999999997. Miller's planet would need to orbit at a radius almost exactly equal to the Schwarzschild radius itself. That's the event horizon, the point of no return. At the event horizon, time dilation becomes infinite. But here's the problem. You can't orbit there. Any planet at that radius would be pulled into the singularity. It would be torn apart. It would cease to exist. So we have a paradox. The physics says we need Miller's planet at the event horizon, but the physics also says nothing can orbit there. So what's the solution? Gargantua is not a non-rotating black hole. It's a rapidly rotating black hole, a Kerr black hole. And when a black hole rotates, something extraordinary happens. It drags space-time with it. This phenomenon is called frame dragging, or the lens-thirring effect. Space-time itself is rotating, creating an effect that's almost like centrifugal force, but for the fabric of space-time itself. Think of it this way. Imagine a whirlpool in space. Not just pulling things in, actually twisting space as it spins. That's frame dragging. The mathematical description is called the Kerr metric. It's more complex than Schwarzschild, but the key new element is A, the spin parameter. It represents how fast the black hole rotates. A equals 0, non-rotating black hole, Schwarzschild. A equals m, maximally rotating black hole, extremal. Cawthorne calculated that Gargantua has a spin parameter of approximately A equals 0.9999 m. That means Gargantua is spinning at 99.99% of maximum possible rotation. At the speed of light, that's approximately 99.9999999% the speed of light. Gargantua is barely holding itself together. And here's where the magic happens. As a Kerr black hole spins faster, the ISCO gets much closer to the event horizon. ISCO means innermost stable circular orbit, the closest a planet can orbit before the orbit becomes unstable. For Schwarzschild, the ISCO is at 6m, 6 times the black hole's mass. For Gargantua, with a approximately 0.9999 m, the ISCO is at 1.2 to 1.5 m. That's a 4-fold decrease. That's enough to bring Miller's planet into a zone where the time dilation factor reaches 60,000. Frame dragging allows space-time to support stable orbits much closer to the horizon. It's as if the rotating black hole is holding matter in orbit through the twisting of space-time itself. And that's how Miller's planet exists. Not through fantasy, through the actual physics of rotating black holes. The time dilation we see in the film isn't just a number, it's a description of space-time geometry. Space-time is so curved near Gargantua that 1 hour of proper time on the planet corresponds to 60,000 hours, about 7 years of coordinate time in the distant universe. For the crew in orbit, 23 years pass. For Cooper on the surface, 3 hours. Barely any aging at all. When he returns, Romilly has become an old man. Cooper is still young. This isn't just physics. This is the tragedy at the heart of Interstellar. Every choice has a cost. Every moment spent saving one world ages another. Time is currency, and the currency is being spent. They land on Miller's planet. Water everywhere, shallow in some places. And then they see something impossible. A mountain the size of Mount Everest, moving, approaching. It's a wave. This is one of the film's most visually stunning sequences, but the physics is equally fascinating. Tidal forces. Just as the moon pulls on Earth's oceans, creating tides, Gargantua is pulling on Miller's planet, but the force is immensely stronger because they're so close. Tidal forces are the difference in gravitational force across an extended object. If the moon pulls on the near side of Earth with force F1 and the far side with force F2, The tidal force is F1 minus F2. And here's the critical equation, the equation that explains the catastrophe. F tidal equals 2gmm times delta r divided by r cubed, where delta r is the size of the object, the planet's radius, and r is the distance from the black hole. Look at that r cubed in the denominator. Tidal forces depend on the cube of distance. If you're twice as close, tidal forces are 8 times stronger. If you're 10 times closer, they're 1,000 times stronger. Miller's planet is orbiting dangerously close to Gargantua. The tidal forces are enormous. The side of Miller's planet facing Gargantua experiences much stronger gravity than the far side. This differential force literally stretches the planet. Water on the facing side is pulled outward. This creates a tidal bulge, essentially a mountain of water. The planet is likely tidally locked. One side always faces Gargantua, but the water is sloshing around due to Coriolis forces and the planet's rotation. Enormous waves form as water is pulled toward the substellar point, the spot directly beneath Gargantua. But here's the question we need to ask. Why doesn't the planet just break apart? Planets are held together by their own gravity, the gravitational self-attraction of all their mass. As long as this self-gravity exceeds the tidal force, the planet remains intact. But it's distorted, elongated. The oceans form massive waves. Miller's planet isn't being destroyed, it's being bent. Now, let's talk about something scarier, spaghettification. In a normal black hole, spaghettification is deadly. The tidal force difference across a human body, from feet to head, becomes so extreme that you're literally torn apart. The name comes exactly from what it sounds like. You're stretched into a strand of spaghetti. But here's the thing, the size of the black hole matters. For a stellar mass black hole, about 10 times the Sun's mass, lethal tidal forces occur far above the event horizon. You'd be spaghettified long before reaching it. For Sagittarius A star, an actual supermassive black hole at the center of our galaxy, 4 million times the Sun's mass, lethal tidal forces occur around 200 AU, farther than Neptune's orbit. For Gargantua, estimated at 100 million times the Sun's mass, lethal tidal forces occur millions of kilometers outside the event horizon. An astronaut could cross the event horizon of Gargantua without immediately being torn apart. They would eventually reach the singularity, where tidal forces become infinite, but they wouldn't be spaghettified immediately. It's why Miller's planet is a death trap, not just because of time dilation, but because everything about it, the tides, the waves, the environment itself, is constantly trying to destroy you. Every moment there is a choice: save the mission or save yourself, and time is running out. Dr. Mann sabotages everything. The airlock blows. The Endurance is suddenly sent into a violent, chaotic spin. The ship is falling, spinning, out of control. And Cooper has to do something that sounds physically impossible: dock with a tumbling, spinning spacecraft while his own vessel is moving at a different velocity and rotation. If you're not familiar with orbital mechanics, this looks like suicide. But there's a beautiful principle underlying this entire sequence: conservation of angular momentum. In space, far from large masses, angular momentum is conserved. The total angular momentum of a system doesn't change unless an external torque acts on it. Angular momentum is calculated as L equals I times omega, where I is the moment of inertia, that is, how hard it is to spin the object, or its rotational mass, and omega is angular velocity, how fast it spins. Here's what this means practically. The Endurance can't simply stop spinning. The explosion gave it massive angular momentum. The only way to stop it is to apply an equal and opposite force, but they don't have time for that. So Cooper has to match the spin. To dock, Cooper must match the linear velocity, falling toward the planet, match the angular velocity, the spin, align the rotational axis perfectly, and position the docking collar with millimeter precision. If he fails any of these, the relative motion will shear the metal, snap the docking mechanism, and send them spinning into the stratosphere to burn up. Now, we have to talk about something that makes every physicist sweat. Case reports the ship is spinning at 67 to 68 RPM. Let's run the math on that because it's terrifying. If the Endurance has a radius of 32 meters and it spins at 68 RPM, which is roughly 7.1 radians per second, the centripetal acceleration at the outer ring is A sub c equals omega squared r, which is 7.1 squared times 32, which is approximately 1,600 meters per second squared. If you divide that by Earth's gravity, which is 9.8 meters per second squared, you get approximately 163 Gs. At 163 Gs, a human body doesn't just pass out, it liquefies. The outer ring of the ship is pulling enough force to crush steel. Bones turn to powder. Organs fail instantly. If Cooper were sitting in the outer ring, he would be dead. Not unconscious, dead. So how does he survive? He docks at the center hub. Look at the formula again. A sub c equals omega squared r. The g-force depends on the radius, r. As you get closer to the center of the spin, the radius drops to 0. At the exact center axis, the g-force drops to 0. It's a bullseye, or death. There's no middle ground. He has to put the ship exactly on the axis of rotation where the forces are survivable. But even at the center, he's not safe. Cooper passes out not because of g-forces crushing him, but because of disorientation. He is spinning at 68 rotations per minute. That's more than 1 rotation per second. This wreaks havoc on the vestibular system, your inner ear's balance mechanism. The fluid in his ears is sloshing wildly, telling his brain he's tumbling in every direction simultaneously. The Coriolis effect on his blood circulation causes massive nausea. His vision creates a strobe effect where he can't process visual data. His equilibrium completely fails. And that's where we find the true heroism. He has to initiate the dock before his brain shuts down. He relies on muscle memory, on Case, on pure adrenaline, on the training that's been burned into his nervous system. He has to hit that center bullseye before the G-forces and disorientation tear everything apart. Every second counts. Every tenth of a meter matters. He's conscious barely enough to make decisions. He's fighting his own body, fighting the physics, and then it works. This isn't just a movie moment. This is a masterclass in rotational physics. It's everything Nolan and Thorne understood about how the universe works, rendered as narrative, as human struggle, as love expressed through sacrifice and skill. Cooper didn't just dock 2 spacecraft. He proved that physics, that mathematics, that understanding the universe can save lives. That's the film's core message. And this scene is where it's crystalline, undeniable.